Screen screen. Start here. We will discuss the inverse and implicit function theorems. Okay. Let us read this concept. That is, consider function f from D to Rn where D is subset of Rn. Note that the domain and range are in having same dimension, Rn to Rn. Okay. Let y equal to f of x. It is a function. Y is a function of x, vector x. Vector y is a function of vector x. Vector y and vector x belongs to n-dimensional space. Some space of the some part of the n-dimensional space. The purpose of this section is to present conditions of existence of inverse function. So we can find the inverse function from the given function. So there should be some conditions. So what are the conditions that we are discussing? Under what condition the inverse exists? So that is given through theorem. Okay, that is usually called the inverse function theorem. So inverse function theorem gives us minimum conditions, required conditions for the existence of the inverse function for a function f from Rn to Rn or f from D to Rn where D is subset of Rn. So note the conditions. Okay, we have to note the conditions for the existence of inverse functions. So there is no proof is given in this text. You can refer that book, book of Sagan, page 371. Okay. So anyway, we are not discussing the proof. We are using only the theorem only. Okay. So
ആൾക്ക് ലിങ്ക് ആക്ടിവേറ്റ് ആവണില്ല എന്ന് പറഞ്ഞു.
നെറ്റ് കുറവുണ്ടായിരിക്കും. ഇനി ഞാൻ റെക്കോർഡ് ചെയ്തിട്ട് അവർക്ക് കൊടുക്കാം കേട്ടോ. Inverse function theorem, that is just state the theorem. Inverse function theorem f from D to Rn, if D is an open subset of Rn. F has continuous first order partial derivatives. That is the first condition. Okay, that is minimum condition for existence of the inverse function. And another condition, if for some x naught belongs to T, the n by n Jacobian matrix is non-singular. Okay, Jacobian should be non-singular. So what are the two conditions? F has continuous first order partial derivatives and Jacobian of f is non-singular. That is determinant of what is Jacobian non-singular. What is non-singular? Non-singularity of matrix. That is determinant of that matrix not equal to 0. So determinant of Jf of x naught, that is denoted as dou f1 f2 etc. fn by dou x1 x2 etc. dou xn evaluated at x equal to x1 is not equal to 0. Where fi is the ith element of f. So what are the conditions? Two conditions. F has continuous first order partial derivatives. Second condition is Jacobian matrix is non-singular. Then there exists an epsilon greater than 0 and a delta greater than 0 such that the inverse function f inverse exists in the neighborhood of f n delta of f of x naught. Okay, and as it takes the values in the neighborhood of and it takes the values in the neighborhood of n epsilon of x naught. Okay, let us draw a figure in the univariate case. This is only in the case of univariate. Similarly, you can consider Rn. This is another Rn. Okay, and suppose we are taking a small region that is D, and we are what is that? We are sending sending the data to from this domain to this region through a function f. Okay, f of x. And here we have the values of the functions. Again, we can consider what is it, a particular point that is denoted as this x naught, in x naught. So consider a particular point x naught. Correspondingly, we can find a function f of x naught. Okay, around this we can find a domain, sorry, a neighborhood around this f of x naught. Okay. Okay. From this neighborhood, you can draw a inverse function. Okay, this is nothing but f inverse അങ്ങനെ എഴുതാം f yes, f inverse of where it is evaluated f of x naught. Okay, so this is the inverse function. So that is the idea. Okay. So in the neighborhood of n of x naught. So that that inverse function should reach it. ഇതിൻ്റെ ഉള്ളിലുള്ള ഒരു ഇവിടെയാണ് ഇതിൻ്റെ ഈ എക്സ് നോട്ട് നെയ്ബർഹുഡിലുള്ള ഇൻവേഴ്സിൻ്റെ വാല്യൂ എടുത്തില്ലേ ഇങ്ങനെയായിരിക്കും. So this is a univariate case. So if inverse exists in the neighborhood of n delta of x and take values in the neighborhood of n epsilon of x naught. Moreover, f inverse has continuous first order partial derivatives in n delta of f of x naught. And its Jacobian matrix of f of x naught is the inverse of jf of x naught. So what is the Jacobian matrix of inverse function? That is nothing but the Jacobian matrix of is the inverse of jf of x naught. So what will be the determinant? Determinant of jf inverse of f of x naught equal to 1 by determinant of jf of x naught. So this is theorem statement only. We don't have proof. So you can conclusion of this theorem. If there are two conditions, that is the first condition, first order partial derivatives. Second is jf of x naught is non-singular. Then inverse exists, and moreover inverse has continuous first order partial derivatives in n delta of f of x naught. And its Jacobian matrix at f of x naught is the inverse of jf of x naught, and determinant of jf inverse of f of x naught equal to 1 by determinant of jf of x naught. So that is the result. Now we can see a problem 2 as an illustration for this theorem. We are considering f from R3 to R3. Here we have x is in the domain, 3-dimensional Euclidean space. Again, this has two components. It 2x1 x2 minus x2 is one component, x1 square plus x2 plus 2x3 square second component, x1 x2 plus x2 third component. Hence jf of x not equal to, you can differentiate with partial dou f1 by dou x1, what is 2x1, dou f1 by dou x2, 2x1 minus 1, f1 by dou x3, there is no x3 here, so we will have 0. So likewise you can find all the partial derivatives. So that will give you what is the determinant. You know the steps involved in computation of determinant. So just find out the determinant, then that will result in minus 12 into x2 x3. Okay, but at the same time, if x1 x2 or x3 is 0, then the determinant will be 0. So we have to keep that x2 and x3 not equal to 0. Then only we will get determinant of jf of x not equal to 0. So at the points in which x2, x3 not equal to 0, that means let us take, for example, domain is equal to x, set of all x1, x2, x3 such that x2 greater than 0 and x3 greater than 0. So there is no 0 point in that x2 is not equal to 0 as well as x3 is not equal to 0. So we can ensure that x2, x3 not equal to 0. So in this domain, we can find the inverse function. Okay, by theorem we can find the inverse. We can find it as from this formulas. This is y1, y2, y3. We can put that here, and from this some rearrangement, using some rearrangement, we can obtain this as x1 equal to y1 plus y3 divided by 2y3 minus y1, and x2 equal to minus y1 plus 2y3 by 3. Just to rearrange these equations. And x3 is equal to 1 by root 2 into y2 minus 2y1 plus y3 square by 2y3 minus y1 square minus 2y3 minus y1 by 3, or x2 1 by 2. So this is a typical example of inverse existence of multivariate inverse function. Okay. For example, consider suppose we are evaluating at a particular point, that is x not equal to 1 1 1 column vector 1 1. Then y naught is exactly equal to, substitute in this formula, and we can see that it is nothing but 1 4 2. And what is the determinant of jf of x naught? That is, put x2 and x3 1. Therefore minus 12 x2 x3 means minus 12 only. Okay. So the Jacobian matrix of f inverse. What is the Jacobian matrix of f inverse? You know the f inverse, f inverse values. Okay, these are the f inverse values. We can find out the Jacobian. So that is 2 by 3, 0, minus 1 by 3, minus 1 by 3, 0, 2 by 3. So let us take the determinant, then we can see that it is nothing but using the the steps involved in computation of determinant. So that is minus by 1 by 12. So from this we can say that here we have minus 12, determinant of jf of x naught, and here also we have, what is that, minus 1 by 12. So that shows the validity of this theorem. Okay. Yeah, you can ask number 7.30. You can say that here we have minus 1 by 12, that is exactly to 1 by minus 12. Okay. So that is an illustrative example. Okay. So that is an example for inverse function theorem. Sometimes we may not be able to express like this. For example, here we have expressed the inverse. Okay, x1 equal to, using some arrangement of these functions, these three functions. Okay, this is, we can express very x1 in the left side, all y's are in the right side. Here x2 is left side, all y's are in the right side, etc. So sometimes we may not be able to express like that. At the same time, they will have some inverses. So we have to address that problem. So the situations in which y is not explicitly expressed as a function of x. So that we have to address. Okay. So for that we consider two vectors, x vector and y vector. X consists of n elements and y consists of m elements. So which is satisfying two conditions. They can write as some function of x and y, g x1 comma xy equals 0. Example, I will show you the example. Yeah, in this example you can see that 80 and yx1 minus x1 x2 plus y. So we can express as g x1 comma y. So in that situation, what happens? So this is exactly what is that we are using in the domain m components and x components and y components. So we will have dimension m plus n. So g from R m plus n to Rn. Okay, 0 belongs to n dimension. In this more general case, we have n equations and m plus n unknowns because we have m plus n variables, n x variables and m y variables, n equations because the range of g is Rn. Okay. So the question is, under what conditions will allow us to solve equations? How can we solve this type of equation? If the inverse exists, that means the if an inverse exists, we can say that the solution exists. Okay, so under what condition the solution exists, or under what condition we can solve these equations? You know, in matrix theory, you know, if there are n equations and n unknowns, you can solve the matrix or solve the matrix equation or solve the linear what is it? System of linear equations. Okay. So equation should be equal to number of variables. So then we can solve. But here that is not true. The number of variables is m plus n and number of equations is n. So we cannot use traditional methods for solving this system of linear equations or system of equations. Okay. So for this for such situations we can use the implicit function for theorem for getting solutions. Okay. So this theorem is also given, but not the proof are not given. It is available in the book of Woods. Okay, you can refer that book. We can study the theorem statement only. If you are interested, you can search for that book and you can find the proof. Or otherwise, if you search in Google, you will get the proof. No implicit function theorem. Let it G from D to R. Where is D? D is open subset belongs to R m plus n. Okay, dimension is m plus n. Okay, G has a continuous first order partial derivatives in D. G has a continuous first order partial derivatives in D. So that is one of the conditions. G has continuous, as in the inverse function theorem. Here also we are imposing the same condition. G has continuous first order partial derivatives in D. Next, if there exists a point z0 belongs to D, where z0 equal to x0 prime, comma y0 prime prime. Okay, if x0 belongs to Rn and y0 belongs to Rm. Okay, such that g of z0 equal to 0. So that point satisfies the equation. That point is a point in the curve g of z. That means the point satisfies the equation g z equal to 0. So g of z0 equal to 0. Okay. If at z0, okay, the next condition is if at z0 dou g1 g2 extra gn by dou x1 x2 xn not equal to 0. Okay, dou g1 g2 etc. We are not differentiating with respect to y. We are differentiating with respect to x only. So dou g1 g2 etc. dou gn by dou x1 dou x2 etc. dou xn not equal to 0. Where ga is the ith element of g. Then there exists a neighborhood n delta of y0 in which the equation g x comma y equal to 0 can be solved uniquely for x as a continuously differential function of y. It is a very wonderful theorem. Because if G satisfies the two conditions, what are the conditions? G has continuous first order partial derivatives in T, and dou G1 G2 x dou Gn divided by dou x1 x2 x not equal to 0. Then what is the result? There is a neighborhood n delta of y0 in which the equation g of x comma y equal to 0 can be solved uniquely for x as a continuously differentiable function of y. So in the neighborhood of n delta of y0, we can solve the equation. Okay, so that is a wonderful result. Even what is the function is represented as implicit function, we can solve that. Okay. We can consider the example. Let us look at this example. This is GR3 to R2, that is represented by Gx1 x2 xy equal to x1 plus x2 plus y square minus h, and second component is x1 minus x1 x2 plus y minus 4. So we have dou g1 by dou g1 g2 by dou x1 dou x2 that equal to, that is exactly equal to determinant of dou g1 by dou x1, that is that dou g1 by dou x1, just one only. Next is dou g1 by dou x2, that is again 1. Second row, dou g2 by dou x1, that is 1 minus x2. Okay, that you can find, and when we compute the determinant, you can see that it is nothing but x2 minus x1 minus 1. Okay, let us take an example at the point 1, 1, 4. That point, we can see that when we substitute in this equation, 1, 1, no, it's 0, okay. At the point 114, we can see that G of is 114 equal to 0. So what is the value of dou G1, dou G2 by dou x and dou x2? That equal to minus 1, not equal to 0. Hence, we can solve that. We can solve these equations by theorem. By using that theorem, this is the minimal conditions required for satisfying the theorem. So by that theorem, we can say that this can be solved. Okay. So uniquely in terms of y in some neighborhood of y not equal to 4. Okay. So we can manually compute the solution, and this will be like this: x1 equal to x1 in the left side, meaning y's are in the right side. x2 in the left side and y's are in the right side. There is no what is that difficulty involved. Just manually think about the rearrangement and just solve this. Okay. And okay. So up to this we have discussed the two theorems. Yes, that one is inverse function theorem, inverse function theorem, and another is implicit function theorem. Both theorems are derived for getting solutions of system of equations. One in the case of, it is that x can be represented in terms of y. Okay. Y can be represented in terms of x. At the same time, in the second theorem, we cannot express y in terms of x. So in that case, we can solve. Okay. That is the two theorems. Okay. Now we move to the next section, that is before that, you can find the, I will show you the maximum minimum result in the book of Bartley. I think you might have studied the maximum minimum conditions, maxima minima theorem, everything you have studied in the univariate case. Maximum minimum theorem.
Yes.
വെച്ചിട്ടുണ്ട്.
Okay, അപ്പോൾ ഈസി ആയിരിക്കും, നമുക്ക് എളുപ്പമാണ്, ബുദ്ധിമുട്ടൊന്നുമില്ല. മീൻ വാല്യൂ തിയറം പഠിച്ചിട്ടുണ്ടല്ലോ അല്ലേ? മീൻ വാല്യൂ തിയറം ഒക്കെ പഠിച്ചിട്ടുണ്ടല്ലോ. Here we can see the results of extreme. When we say that a function is increasing, a function f is said to be strictly increasing on the interval I if for any 2 points x1 comma x2 in I x1 comma x2 less than implies f of x1 less than f of x2. Here you can see a figure that is f of x is increasing. When we say that f of x is increasing, x1 less than x2, then f of x1 less than f of x2. Okay, that is the concept of increasing. Similarly, in the case of decreasing functions, we can say that when x1 less than x2, f of x1 greater than f of x2. First derivative test for extrema. Let us recall this result. Okay, let it be a continuous interval I from I equal to positional AB, and let's see an interior point of I. Assume that f is differentiable. Then, what is the result? If there is a neighborhood c minus delta comma c plus delta belongs to I such that f dash of c greater than or equal to 0. If the first derivative is positive and f dash in the region c minus delta less than x less than c, and f dash c is less than 0 for c in the right side, c less than x less than c plus delta, then f has a relative maximum. Okay, relative maximum. I will show the figure. Yeah, you can see here you can see the relative maximum. There are several figures here. You can see that. Yeah. In this case, let us discuss. Here, so in this case, in this figure, you can see that the function goes like this and approaches a maximum. So and again in the right side you can see it is going. So here in this part you have f dash of c less than 0. In this part you will have f dash of c greater than 0. So this is a relative maximum. Again, this is a relative minimum. That means in the left part you can have f dash of c less than 0, and in the right part you can have f dash of c greater than 0. So this is relative minimum. What is absolute maximum? Yeah, this is in this part, and this is the maximum. Maximum for when we consider the entire function, you can see that it is the entire maximum, absolute maximum. If there is a neighborhood such that f dash of c less than 0, as in the second case, dash of c, f dash of x less than 0 on the left side, and f dash of c greater than 0 on the right side, then that is of course a relative minimum. I'm not going to the proof everything, just recalling the results. Okay. Another result, you can see that let I be an interval and f from I to c, I to r, and c belongs to I, and assume that f has a derivative at c, then f dash of c greater than 0, then there exists a number delta greater than 0 such that f of x is greater than f of c for x belongs to I, such that z less than x less than c plus delta. And if f dash of c less than 0, at the point c, if f dash of c less than 0, then there exists a point delta greater than 0 such that f of x greater than f of c for x belongs to, that means f of c will be minimum, okay, where c minus delta less than x less than delta. So that means what is the meaning? The function will be higher at the point x, where x is the point in between c minus delta and c, and the minimum value occurred at c. So that means the function will be a decreasing function. Okay. The result proof there. Okay. Okay, that much results we require only for discussion of this session. Okay. What is stated here? Let f of x be a real valued function defined on a set or D subset of Rn. At the point x naught belongs to D, at a point x naught belongs to D is said to be a point of local maximum if there exists a neighborhood n delta of x naught subset of D such that f of x is less than or equal to f of x naught. That is, in that smaller region, in that neighborhood, f of x naught is maximum, as we seen in this field. This is universal case. Let us see by if there exists. So in this, this is relative maximum. Okay. So when we consider the smaller region, you can see, when we consider this small domain, you can see this is the relative maximum. So f of x naught is greater than or equal to f of x in that region only. When we consider the whole region, we cannot say that is maximum. Okay. And similarly, if f of x is greater than or equal to f of x, and for all x belongs to n delta of x naught, then x naught is point of local minimum. Okay. Local minimum, you can see, yeah, this is local minimum. Yeah, this point is local minimum. Let us search for another example. Here we can see local minimum. Here also we can see that these are local minimum in this region. These are also local minimum. So there are several figures available. You can, so these are all local minimas. Okay, these are all local minimas, but this is local maximum. This is local maximum. This is local maximum. Okay, so similarly you can find, this is the theoretical concept. F of x greater than or equal to f of x1 for x belongs to n delta of x1. If one of these inequalities holds for all x in D, so if we consider entire region, so if it is maximum in the entire region, then we can say that x0 is a point of absolute maximum. Okay, not local, it is absolute maximum. Okay, or a point of absolute minimum. Okay, what will be the case we are discussing? If it is less than or equal to, so that is absolute maximum. If it is greater than or equal to, then it is absolute minimum. Okay. Commonly, it is known as optimum or extremum. Okay, optimum or extremum. So that are the names we are using. We have theorem that we'll discuss in the next class, no problem. Anyway, in that theorem, we will discuss the necessary and sufficient condition for the existence of what is that point of maximum, point of minimum, saddle point, etc. So that we will discuss in the next class, no problem, because it has this is a long proof, so we have to discuss in detail. Okay, anyway, let us stop here. And this theory is very useful in the matrix analysis, matrix theory, and statistics, especially in the case of what is that multivariate statistics. So these theorems are very useful, very important. Anyway, I would like to give some seminars also. I will help you to discuss these theorems and corollaries, no problem, to this example. And you can take the next session. What is the next session? The method of Lagrange multiplier. Okay, you can discuss this method. I think one of you can study this, and what is that? You can take a seminar in the next week, because in the next week I have examination because I am Parisha Sober, so I may not be able to what is that discuss in detail. So, but at the same time I can listen what the discussions from you. Okay, so I cannot handle the computer and everything, but at the same time I can listen using my mobile phone. So you may prepare this theorem. Okay. Record തരാൻ പറ്റുക